Hello students, let me introduce you to the chapter Limits and Derivatives. In this chapter, we shall look into the introduction, intuitive idea of derivatives, limits, limits of trigonometric functions and derivatives. Let us begin with the introduction. The invention of calculus was one of the most far-reaching events in the history of mathematics. It is that part of mathematics which mainly deals with the study of change in the value of a function as the value of the variable in the domain range. Calculus has a wide range of uses in sciences, engineering, economics and in many other walks of life. It is extensively used in graphical work, including the calculation of the slope of tangent to a curve at a point. This chapter is an introduction to calculus. In this chapter, we shall introduce the concept of limit of a function, study some algebra of limits and will evaluate limits of some algebraic and trigonometric functions. Then, we shall define the derivative of a function, give its geometrical and physical interpretations, study some algebra of derivatives and will obtain derivatives of standard functions. Now, let us have some intuitive idea of derivatives. Physical experiments have confirmed about the body dropped from a tall cliff covers a distance of 4.9 t square meters in t seconds, that is, distance s in meters covered by the body as a function of time t seconds is given by s is equal to 4.9 into t square. Look at the table on your monitor. It gives the distance travelled in meters at various intervals of time in seconds of a body dropped from a tall cliff. The objective is to find the velocity of the body at time t is equal to 2 seconds from this data. We can find time in seconds and distance in meters, and 1 second 4.9 meters distance is covered. At 1.5 seconds 11.025 meters, at 1.8 seconds it is 15.876, at 1.9 it is 17.689. As you approach to 2, 1.95 seconds 18.63225 meters, and at 2 it is 19.6 meters. One way to approach this problem is to find the average velocity for various intervals of time ending at t is equal to 2 seconds and hope that these throw some light on the velocity at t is equal to 2 seconds. Average velocity between t is equal to t1 and t is equal to t2 equals distance travelled between t is equal to t1 and t is equal to t2 seconds divided by t2 minus t1. Hence, the average velocity in the first 2 seconds is given by distance travelled between t2 is equal to 2 and t1, that is 0 seconds, upon time interval t2 minus t1, that is equal to 19.6 minus 0 meters upon 2 minus 0 seconds, that is 9.8 meters per second. Similarly, the average velocity between t is equal to 1 and t is equal to 2 seconds is 19.6 minus 4.9 meters upon 2 minus 1 seconds, that is equal to 14.7 meters per second. Likewise, we compute the average velocity between t is equal to t1 and t is equal to 2 for various values of t1. The following table gives the average velocity v, t is equal to t1 seconds and t is equal to 2 seconds. You can see here t1 is varying from 0, 1, 1.5, 1.8, 1.9, 1.95 and 1.99 seconds, and accordingly the velocity is 9.8 meters per second, 14.7 meters per second, 17.15 meters per second, and as it is approaching 2, it is becoming 19.551 meters per second. From table, we observe that the average velocity is gradually increasing as we make the time intervals ending at t is equal to 2 smaller. We see that we get a better idea of the velocity at t is equal to 2 seconds. Hoping that nothing really dramatic happens between 1.99 seconds and 2 seconds, we conclude that the average velocity at t is equal to 2 seconds is just above 19.551 meters per second. This conclusion is somewhat strengthened by the following set of computation. Compute the average velocities for various time intervals starting at t is equal to 2 seconds. As before, the average velocity v between t is equal to 2 seconds and t is equal to t2 seconds is given by distance travelled between 2 seconds and t1 seconds divided by t2 minus 2, that is equal to distance travelled in t2 seconds minus distance travelled in 2 seconds divided by t2 minus 2, that is equal to distance travelled in t2 seconds minus 19.6 upon t1 minus 2. The table on your monitor gives the average velocity v in meters per second between t is equal to 2 seconds and t2 seconds. Here in the table you can note t2 is 4 seconds, velocity is 29.4 meters per second. When it is 3 seconds, it becomes 24.5 meters per second. For 2.5, it reduces to 22.05 meters per second. For 2.2, it is 20.58 meters per second. 2.1, it is 20.09 meters per second, and as it is approaching 2, it is becoming 2.01, 19.649 meters per second. Here again we note that if we take smaller time intervals starting at t is equal to 2, we get better idea of the velocity at t is equal to 2. In the first set of computations, what we have done is to find average velocities in increasing time intervals ending at t is equal to 2, and then hope that nothing dramatic happens just before t is equal to 2. In the second set of computations, we have found this average velocities decreasing in time intervals ending at t is equal to 2, and then hope that nothing dramatic happens just after t is equal to 2 seconds. Purely on the physical grounds, both these sequences of average velocities must approach a common limit. We can safely conclude that the velocity of the body at t is equal to 2 seconds is between 19.551 meters per second and 19.649 meters per second. Technically, we say that the instantaneous velocity at t is equal to 2 seconds is between 19.551 meters per second and 19.649 meters per second. As is well known, velocity is the rate of change of displacement. Hence, we have accomplished is the following. From the given data of distance covered at various time instants, we have estimated the rate of change of the distance at a given instant of time. We say that the derivative of the distant function s is equal to 4.9 into t square at t is equal to 2 is between 19.551 and 19.649. An alternate way of viewing this limiting process is shown in the figure on your monitor. You can see the figure here. This is your time axis taken as x axis, and this is y axis showing you the distance, and this is the graph of s is equal to 4.9 t square. We have studied the position of the body at 2 seconds, and it is denoted by point A, and 2 plus t2 seconds the body has covered the distance of b2, and similarly 2 plus t1 it gives you the point b1. This is a plot of distance s of the body from the top of the cliff versus the time t elapsed. In the limit, as the sequence of time intervals h1, h2 and so on approaches 0, the sequence of average velocities approaches the same limit as does the sequence of ratios. That is C1 B1 upon AC1, C2 B2 upon AC2, C3 B3 upon AC3 and so on, where C1 B1 is equal to S1 minus S0 is the distance travelled by the body in the time interval H1 is equal to AC1, etc. From the figure, it is safe to conclude that this latter sequence approaches the slope of the tangent to the curve at point A. In other words, the instantaneous velocity v t of a body at time t is equal to 2 is equal to the slope of tangent of curve s is equal to 4.9 into t square at t is equal to 2 seconds. Now, students, to have an idea about the derivative, let us take a function f, real valued function, the function denoted by limit f of x plus h minus f of x upon h as h tends to 0, wherever the limits exist is defined to be the derivative of t at x and is denoted by f dash x. This definition of derivative is also called the first principle of derivative. Hence, f dash x is equal to limit f of x plus h minus f of x upon h as h tends to 0. Sometimes f dash x is denoted by d by dx of f of x, or if y is equal to f of x, it is denoted by dy by dx. This is referred to as derivative of f of x or y with respect to x. It is also denoted by d of f of x. Further, the derivative of f at x is equal to a is also denoted by d by dx of f of x at a, or df upon dx at a, or d by dx at x is equal to a. So, students, today we had an intuitive idea of derivatives. In the next session, we shall study about limits. Thank you.